to the last speaker, the Rafael. Yeah, I hear you, right? Yeah, let me
Yes.
introduce him a little bit. And Rafael is an electrical engineering and Master of Science from the University Atmosphere of Nuevo Leon, Mexico, in 2004 and 2007, respectively. And then he spent 1 year at ABB in Switzerland. And after that, he got his PhD degree at Imperial College London. And, and after that, he was a postdoc fellow at the KTH. And since summer 2014, he has been a research associate at the Zurich University of Applied Science in Switzerland. And he is a senior member of the IEEE and also the chair of the annual international workshop, Dam Power, and I also attend that one, a really good one. And he is also the chair of the IEEE task force focused on the application of big data analytic on transmission system dynamic security assessment. He is also the leader of working groups in different power system programs in Switzerland. Some of his areas interests include control, dynamics, stability, and quantification of the impact of renewable energies in large transmission network, as well as data analysis techniques in advanced military infrastructure. So welcome him to give us the speech focus on the coherency identification based on dynamic reduction of frequency measurements. Welcome, Rafael. It's your turn.
Thank you very much, Jali. I just want to make sure that I'm sharing the right screen. Can you see my main screen?
Yeah, very clearly.
Okay, thank you very much. So it's a honor to me to be a speaker in this prestigious panel and this conference. Thank you very much for the invitation, Jali, for the organization of such event. I have divided my presentation in these 4 points. I'm a bit lighter than my previous colleagues, and due to the time now, I will try to be brief and more straight. So thank you very much. So first, I want to talk about the motivation, but not only for this particular work that I'm presenting today, but also the research directions that motivate the programs and the activities that we are doing here in Switzerland and in general in Europe. Then I want to describe specific applications of dimensionality reduction technique that we have applied for frequency measurements, and then show a study case using the dynamic model of continental Europe, and then just close the presentation with a summary and conclusions. So as we all are very familiar now that everyone is aware about the climate change that we're experiencing, and particularly the younger generations are very critical and very active about this situation. According to some official data from international agencies, the temperature in most parts of the planet has been rising about 2 degrees considering from the introduction of industry in 1900. So based on information from the international agency, the growth in the global CO2 emissions is reaching now historical levels, and we can see that the trend has been growing without seeing the reduction on these emissions. So for this reason, developed countries are now everyone implementing ambitions and aggressive energy transitions like those we have heard today from my colleagues in the different panels. So the goal in Europe is to achieve some zero emission power system by approximately 2050. And they have some specific targets which include that the expected contribution from wind um, production is about should be about 45% and 18% from solar by 2040. This is information that can be extracted um, from places like ENSO-E, which is the regulator of the transmission systems in Central Europe. Um, so the energy transitions are already happening. It's not something that we have to wait to see. And the technical cost for the successful application of these implementations is the some technical challenges for the engineers. So in order to have a system which provides 70% of the load, of the total load by renewable energies, this represents that the system should rely on the cross-border exchange between the neighbor countries, which means that the transmission capacity should be increased and new interconnections should be developed, probably by HVDC links. So as a consequence um, of these technical challenges, then the already complex machine that the human have built to bring energy to the society is expected to become even more complex to or difficult to manage in real time. New challenges emerging from these transitions who aims or to push for renewable energy sources will also introduce problems like the reduction of the inertia in the system, and then for instance also the problems related to the massive use of power electronic devices in the network, among other problems that we can mention. And what is important for our panel today is also that reinforce what Professor Vladimir was mentioning in the first talk. So is that much more data is collected now across the network, which needs to be stored and analyzed for the benefit of the operators and all the players in the electrical energy market. So just to mention that even though in the European power system is one of the most robust electric power systems that exist now, still subject to unforeseen events. And this is a picture from the one of the most recent important events who happened in January 2019, where the European power system, the Central European power system, experienced a severe frequency deviation of about the maximum peak of almost 200 millihertz. And this was caused by a technical failure measurement of four tie lines connecting Germany and Austria, affecting the low frequency control within the Central European power system, which led to long-lasting significant frequency deviation. This frequency deviation was for about slightly more than 5 minutes, and the result was the time deviation of up to 84 seconds in different clocks around Central Europe. So also, on the other hand, it's a very exciting time to be an electrical engineer, where new research opportunities are arising, has been said already. So we are making a transition to a digital power system, a more digital power system, and There is a lot of work to do related with the digital solutions that need to be implemented, specifically also with the installation of this smart metering infrastructure at distribution and transmission level. At the cybersecurity constraint is it's important to deal now, and the managing of the data in terms of storage, visualization, and compression of this information that we are receiving. Similarly, now this industry aims for new solutions to provide a secure operation of the future power grid, and particularly there should be explored the definition of stability in this with the new players in the system, the redefinition of protection schemes such as the under frequency load shedding control, the exploration of virtual inertia, the increase the flexibility on the system, and analysis of the power quality due to the massive introduction of power electronic components and so on. And finally, but not least, we should not forget about the market domain, where it's important to notice that new players for provide ancillary services and frequency support are now emerging from the distribution side, which can now provide support to the transmission system operators. And this link needs to be well defined in terms of policy, economically and technically challenged to improve or to support the secure operation of the overall system. So now I'm going to very briefly introduce one of the research activities we are working in the group where I belong. And the idea is that, or the goal of this type of work we are doing is that we want to find added value to the available data, in particularly at the transmission level, where we are interested in PMUs and how to support the decision making for transmission system operators. So this work has been developed along these lines, and it has been, what I'm presenting now is it's in the early stage of this research, which is still ongoing. So what we have done is that we need to start a starting point. We have frequency measurements from at different points of transmission system. In this case, we are performing RMS simulations with a dynamic model from continental Europe. And then based on these measurements, propose an innovative data dimensionality reduction technique, which is not proposed by us, but which what we are trying to achieve here is to bring ideas which have been successful in different fields to power system applications. And in this particular case, we want to find the groups of machines participating in a given contingency. And on top of that, complement the analysis with the proposal of metrics or indicators who can give additional information about the participation, in this case, of the machines in a given fault. So the dimensionality reduction techniques, we can find the family of linear approaches, which has been successfully applied, such as this principal component analysis and the others linear techniques. And they have been very popular use because it's relatively simple to use, and there's not much information that we need a priori to use these simple tools. However, the drawbacks of this linear family of the dimensionality reduction techniques is, I would say, the most important one is the visualization of the results when the set of data becomes larger and larger. And obviously that it's not possible to use in nonlinear data sets. So we propose in this case the application of a nonlinear method, which is referred as this T-distributed stochastic neighbor embedding, which has been successfully applied in other fields like medicine or for human behavior, in medicine for particularly for breast cancer analysis, and has not been fully explored for power system applications. And therefore and it has it's quite powerful for visualization of clusters. That's why we try to play with this technique and see how successful we could be applied for power system applications. So it's in a general description. So given the starting point is original data sets, which in this case are frequency measurements, which can be coming from a PMU, phasor measurement unit, or in our case from an RMS simulation. And then the final objective is to reduce the dimension of these data sets using this nonlinear technique. So in principle, what we have to do first is to convert all the Euclidean distances into conditional probabilities, and then calculate the output space coordinates with a conditional probability, and finally use a cost function which will be minimized. Um, so the European power system today, it's integrated by 5 different asynchronous areas, where we focus on the blue system here, which is the Central European power system, which has been widely known to have 2 inter-area modes who oscillate against each other of low frequency from typically the east-west machines, and then the north-south machines. And then in 2010, Turkey was integrated to this already large power system, introducing a new mode into the Central European system. So what we use for our analysis is this the only dynamic model which is now available for this particular part of Europe, Central Europe. The model has been developed by the regulator of all the transmission system operators in Europe, which is called ENTSO-E, and it comprehends 26 countries, and it's available in the commercial software Dick Silent Power Factory. And as we can see from the table, the model is quite challenging. It has more than 20,000 buses and 6,000 generators, but this number includes the representation of static and synchronous machines. So we have used this as the system for testing show the demonstration of this technique for the identification of coherent generators. So to illustrate this, what we did was we select 4 countries, which are described here. And the reason we choose only 4 is that these are the countries which are modeled in more detail, and they together have, or individually, are the countries who have the most of the synchronous machines on the system, more than 600 synchronous machines. And then what we did to apply a disturbance was we remove a large synchronous generator in France, representing a loss of 1.4 gigawatts on the system, and then collect the frequencies on this on all the buses from these 4 countries and observe the results. So here is one of the simulation outcome of the RMS simulation. And by just visual observation, we can see very broadly that the machines already show that they converge in three different groups. So after application of the traditional approaches like the principal component analysis and ISOMAP, we could see that these linear approaches cannot see much more than that. So principal component analysis detect 3 clusters, ISOMAP only 4. But with the proposed nonlinear approach, we can see that we can see up to 8 clusters, different clusters. I have to mention that these groups can be calculated in a recursive way using windows, time windows, which means that we could apply this technique in real time, which is the next step that we is following this approach. And we can calculate the clusters also across the evolution of the time of a given fault. So what we can see from here already is that this nonlinear technique can identify smaller groups even when the variation of the input is small, while these classical methods cannot see these variations. This is one of the important pictures to understand what we have done here. So we have divided the simulation in two windows here. So first we have the post-fault part until 20 seconds, which is about the time where the system is experiencing just the inertia response or the natural inertia response from the system. And then the window time where we can see the reaction from the controls of the system. And the result from the nonlinear application of this technique to these two different parts windows is showing in these two B and C diagrams. And we can see that just after the fault, how the groups of machines geographically have been distributed. So we have basically two big groups in the east-west side, Turkey and Spain area. And then the rest of the groups are distributed in the Central Europe in small subclusters. And then after the controls have reacted, we could see that mostly two groups where the machines from Turkey are oscillating against the rest of the groups. And we can identify that still the 8 groups, but they are basically in phase, the rest of the groups against Turkey. And to be able to see this phase and interaction, we have provide this additional metric, which is similar to the participation factors that can be found in the literature. However, this measure has been calculated using the outcome of the proposed dimensionality reduction technique, this subset of reduction of data. And we can ultimately plot in a polar plot the magnitude and angle of the different subgroups, and we can confirm what we are seeing in the simulation. So basically, how the phase of the groups it's changing and between them, and how why the groups look here that they it's only 2, but in fact there's still the 8 there. So this is my presentation. Some conclusions very quickly is that we are in energy transitions all around the world, and this is calling for innovative solutions in the power systems. The data analytics for applications on energy system is fundamental, and the main goal is to incorporate or find the added value of the information that we already have. I have presented this dimensionality reduction technique nonlinear for frequency measurements. In this case was offline application, but this could be extended to online application. and it has been compared with the classical methods. And the main outcome is that this nonlinear technique can find small variations in data sets, something that could not be observed with the linear traditional approaches. And yeah, as mentioned before, we have to extend this in online mode, which we almost done with this part, and we'll be happy to present this in a future opportunity. And we equip also the integration of this technique of power system with new global measures to find the interaction of these groups in relation to a given contingency. Finally, I just want to take the opportunity to invite everyone who is interested in the activities that we are doing in this task force that I have the pleasure to lead, also with the co-participation of Yan Li. And we are doing very interesting things with a very strong group of people around the world. And I just want to invite you to visit the website and maybe join the meetings in the future. Without taking more of your time, I would like to thank you, Jan Lee, for the invitation and everyone for their attention. Thank you very much.
You are muted.
Sorry, can you hear me? Okay.
Yes, now.
Yeah. Here are 3 questions for you, Rafael. Thanks a lot.
Yes, let me scroll down. Okay. What other problems
The first
in our
one,
system?
yeah.
By this approach, what other problems? Well, it is not problems what it will be solved, but the advantage of this approach is that you can visualize data in a better way than that linear approaches. So it can be integrated in any application that you might need. You have large data set that you might need to visualize, not in dendrograms or in a better way. I would suggest that this will be a good tool to apply. So the next question from Professor Terces: can the location of the perturbation affect the shape number of clusters? And then will synthetic virtual inertia have an impact on the creation of clusters? It's not always the same, but depends. Yes. Yeah, the location definitely has an impact. We have more or less investigate this, and for a given power system, in some places the fault location might not excitate the modes or the machines in the same way, and we might not see high observability of the phenomena. So the location is critical, yes, and the virtual inertia, I would say that also might affect because integrating the virtual inertia, we are definitely changing the dynamic of the system. And this is, I think, an important topic to see if how the virtual inertia might affect the poles of the system, or how much it can be affected by the introduction of virtual inertia at certain extent, because probably with not so much virtual inertia, it will be the same effect as having lack of inertia, which for instance, in Switzerland, when we are removing synchronous machines by decommissioning nuclear power plants, but since it's interconnected in the European Central Power System, the effect is not that visible, but we can try to compare how much, at what extent the lack of inertia will have an effect. So in the same way, I would say that the integration of virtual inertia, at what point it will be relevant for the changing the dynamics of the system.
Rafael, I fully agree with you, and I like your answer. And the question is very complicated indeed, because the whole grouping and clustering, it has to do with inertia. Because frequency versus inertia, active power, that's the key strong relationship. And if we dynamically change inertia of the system through synthetic inertia, then we will, interestingly, we will definitely change the shape of new clusters. And you can just imagine, when changing dynamically the synthetic inertia, we will also, in the similar way, maybe dynamically change the shape, even the number of clusters. This is an open questions. You can address them and try to do research. I will also ask my researchers to work on this. That's very interesting. Thank you very much for this presentation.
No, thanks for the comment. It's something that definitely needs to be something done, and there's not an answer right now.
Okay, thanks a lot, Rafael. I think maybe that's the end for your part. And sorry a little bit for the time delay, but I can tell that that's a really hot topic and everybody are really interested in this one. So I want to thanks again for joining our panel. And I think if you have any further comments, questions, or advice about this topic, welcome to contact any of us. And meanwhile, I will collect the slides of each speaker and share it through the organization committee. You can see the detailed information. And I think maybe that's the end about our panel. And thanks a lot. And looking forward to see everybody in future face to face. So hope everybody are well. Okay.
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 Yeah.
Thank you. Thank you very much.
Thank you.
Thank you. Thank
Yeah.
you.
Bye.
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 Bye. Bye. Bye. All the best.
Thanks, Professor Yan. Bye.
Thanks.
Bye.
Thank you.